Okay, welcome back everybody. The first thing I want to mention is that the second exam is going to be next Friday. Everybody will be here. So next Friday is an A-B day. Everybody will be in the room. Be sure to bring a mask, cover that nose, sir. Yeah, get a different mask if it keeps popping down.
Yeah, Bree said, can I use your marker real quick to just show you off my name?
You can take, just grab something there.
Okay, thank you.
Be sure to bring your mask and be sure to keep your nose covered. If you know, masks are available free over in the Lane Center. Did you know that? So go over to the Lane Center and get a free mask. They're better than these paper things that slide down when you open your mouth, okay? Yeah.
Thank you.
Try not to touch it. Anyway, it'll be the same format as the previous exam. There'll be multiple choice, there'll be matching, and there'll be an extra credit essay question, okay? There is a review sheet that people today can pick up here in class. The rest of you can pick it up on Monday. And I'll also send out an email with it attached in electronic format so you can save it in your phone and review it whenever you want, okay? It will be on the subjects of entropy, which we're just getting into, and energy. All right? That said, let us continue. Last lesson, I got up to the Watt steam engine. And the Watt steam engine was the first commercially successful steam engine. The new common engine was around. The new common engine was in use, and I got to tell you, if you can go to Michigan and go to the Henry Ford, they just call it the Henry Ford Museum, fabulous place. They have a real new common engine there. You can see what it's like. It was usually commercial stuff, but commercially successful means that it was widely used, and that was the Watt engine. The reason was the efficiency. And we mentioned that efficiency is the fraction of heat converted to work. Really, we call it the percentage, right? The percentage of heat converted to work. A heat engine is an energy converter. And the more of the heat that is converted into work, then the less fuel it's going to use, and also the smaller it is going to be. So the more efficient you make the heat engine, the smaller it can be, and the less fuel it will use. So what you want to do, just like cars, is you want to maximize the fuel efficiency, while at the same time having an engine that doesn't blow itself up or something like that. So there's always compromises involved, always, okay? And so if we write this out, the efficiency of any engine is defined as the work out divided by the heat in times 100%. It's the percentage of heat, let's just say it's the percentage of heat converted to work. Either way, I guess you could say fraction. But the fraction times 100 is the percent, okay? What we would like this to be is 100%. We would love to have this be 100%. If I could make a 100% efficient heat engine, I could put it outside my house, have it draw in heat from the outside, even on the coldest winter day. The very coldest winter day is way above absolute zero, so there's plenty of heat outside, even on the very coldest winter day. Have it convert that into mechanical energy, have that drive a generator, and I could run my house electrically, including the heat, and never have to buy any energy from any of the energy companies. I could charge my electric car, I could use my electric water heater, my electric lights, my electric heating. I would never have to buy any energy from anybody. As we are going to now see, it can't be 100% efficient. And it sure the hell can't be more than 100% efficient. I always like it when people say someone gave 105%. That's bullshit. You can't do that. You can give your all and that's it. You give your all, and that's it. You cannot have more work coming out than heat went in, because that would mean you created energy, and that violates the first law of thermodynamics. You can't do that. You cannot do that. 100% is the best you can, and today we are going to see that you can't even get 100%. In fact, it's pretty lousy. In fact, if you go to, one second Dylan, if you go to a current power plant that, say, burns coal and generates electricity, only about 40% of the energy in the coal, now the coal is chemical energy, only about 40% of that makes it onto the power grid as electricity. The other 60% remains as heat and goes up the cooling tower. Dylan?
So, like, what's really the difference, like, with, like, the solar panels?
Solar panels, the efficiency of solar panels, they're not heat engines.
Oh, okay.
Solar panels convert radiant energy into electricity. The energy coming from the sun is not heat. It's radiant energy. Now, when it hits the surface of the earth, it's converted into radiant energy. Some of it is sent back off into space. I mean, when you look at the earth from outer space and see the sunlight coming back, that's energy that was bounced off. The rest of it becomes heat. Or in some cases, it's turned into gravitational potential energy. That's how the water gets up into the clouds. But in a solar cell, the best solar cells at the moment are about 25% efficient, which means they can only convert about 75 or 25% of that solar energy into electricity. What happens to the rest? Gets turned into heat. You're going to see heat seems to come all the time. And now you're going to see why. So, the question is, how do you make the most efficient heat engine possible? If you're going to build a heat engine, a steam engine, how do you make the most efficient one? Yes, sir. Speak really loud. The work that comes out.
Oh, okay.
Sorry. Yeah, the workout. The work that comes out divided by the heat that went in times 100%. So a 50% efficient engine means that half the heat got converted into work or mechanical energy, electricity, whatever, and the other half remained as heat.
So I guess increase.
So what we want to do is to increase the work coming out. How do we operate the engine such that we increase the work coming out without increasing the heat going in? That's what we need to do. Now, in 1824, a book was written by a Frenchman named Sadi Carnot called On the Motive Power of Fire. I have a copy of that book. And it's a long book, but in it there are 4 principles which we now call the Carnot cycle, which detail how you should operate a heat engine such that it's as efficient as possible. Now, as I said, a heat engine doesn't have to be anything that is mechanical. In my workshop at home, I got them surplus. I have a couple of these little tiny little squares. They're about an inch square. And if you make one of them hot and one of them cold, it'll function as a battery. It will directly take heat and convert it into electricity. No mechanical generators and stuff like that involved. It's very, very inefficient. Very inefficient. But it directly converts heat into electricity. That is a heat engine. So it doesn't have to have moving parts even. But the one I'm going to show now does have moving parts, and it's based on a gas engine. Okay? So, the Sadi Carnot in 1824 is able to derive a heat engine cycle. Now, the word cycle means to do over and over and over again. It means a cycle, something that you can repeat over and over and over again. The heat engine cycle for the most efficient heat engine possible. This is correct, by the way. It is possible to use the mathematics of calculus to mathematically consider this and find out what must you do to maximize or minimize something. This is very common in calculus. So this is a strict theoretical look at a heat engine, and he comes up with a cycle for the most efficient heat engine possible, which we call the ideal heat engine. So this is the cycle that you use to make an ideal heat engine. No engine can be more efficient than this. It is not possible to have an engine that is more efficient than an engine that is using Carnot's principles. This is still correct. 1824. He uses, by the way, the caloric theory. We know the caloric theory is wrong. He doesn't use the kinetic molecular theory. He doesn't know that heat is random, disordered molecular energy. He doesn't know that. Nonetheless, the caloric theory is good enough that it gives him the correct cycle. Now he calculates the efficiency of his engine, and he gets it wrong. The number that he calculates for the efficiency is wrong because he uses the caloric theory. But the steps in the cycle turn out to be correct. It isn't until about the middle of the 1800s that they get the efficiency correct, because then they understand that heat is a form of energy, and what he has caloric flowing through the engine like a water wheel, and then energy coming out. We know that's not what happens. We know that energy goes in, some of it gets converted, and some of it goes out. But the steps in the cycle are correct. And they have a profound result. Theoretically and philosophically, there is a profound result from this. Did I turn on the microphone?
I mean, the red light's on, but I don't know.
I'll just cut that little piece out there, okay? Where am I at? Caloric theory. I just got to watch that when I do the editing. Okay, so what does he come up with? What is the theory? What are the steps in this cycle? Well, to represent the engine, we are going to use a gas engine, an engine that uses some kind of a gas inside of it. Okay? It could actually be air. It doesn't have to be steam. It could be air. And there are air engines out there. I have one in my shop that I built. It uses the same bit of air over and over again. It's not a Carnot engine, but you can't actually build a Carnot engine, because a Carnot engine is the ideal. It's what you try to emulate. The ideal is what, and nobody is the ideal. Nobody. Nothing is the ideal. You try to get there. Okay? So here's what we got. We start with step one. And this is called the Carnot cycle. And I don't make any promises, but this is an excellent essay question. Describe the Carnot cycle and what goes on. There's a great one. Or describe the Watt engine, or describe the Newcomen engine. Okay? Step one. We have a cylinder. It's a piston type engine, though a turbine could be a Carnot engine. Okay? It doesn't have to be. We have a piston and cylinder. So in here is a piston, which can slide back and forth. It is connected to a flywheel. This is all in the textbook. Nice drawing in the textbook. And there is some sort of working gas in here. And we know that those molecules are bouncing around in random disordered motion. Random disordered motion. The cylinder is insulated. The cylinder is fully insulated. And it has a back door that can be opened and closed to let heat in and out. An insulated door that can be opened and closed. What Carnot says is, first of all, if you're going to convert heat into energy or heat into work, you've got to put heat into the engine. You load it up. So we will draw a candle here to represent the heat source. So our candle just represents the heat source. Now, here's the problem. When you have a heat engine, we are going to quickly see that you must have a difference of temperature. You must have heat at two different temperatures. This is like saying, if you want to use the potential energy in water, you must have water at two different heights. You cannot operate a water wheel unless the water is at two different heights. You can have a huge lake full of water, but unless you can let the water run out to someplace else, you can't run a water wheel. So you must have heat at a higher temperature. We call that the hot reservoir, or TH. This is called the hot reservoir. It could be actually to us cold. Remember, hot and cold are to human beings over a very limited range. It's always amazing how right now we say, man, it went all the way down to 40 last night. Wow. And then in 2 months we say, wow, it went all the way up to 40. Okay? So you have to have a difference of temperature. TC is defined as the cold reservoir, a place where things are colder. Okay? And we are going to see that having a difference of temperature is a critical thing. You must have a difference of temperature to run a heat engine. We're going to see this. So, here's our hot reservoir. We let heat go into the engine, but here is what you must do according to Carnot. You must allow heat to go into the engine, but you must do it such that the temperature does not rise or fall. You've got to put heat into the engine, but you can't allow the temperature to change. You can show with calculus that if the temperature goes up or down accidentally, it won't be as efficient in the end. Isothermal, remember, means constant temperature. We talked about that with phase changes. So here's what's going to go on. If you just try and heat this baby, you're going to make the temperature of that gas go up because you're going to make those molecules go faster. Remember we said the average kinetic energy per molecule is proportional to the absolute temperature. So how can you prevent the temperature from going up? Let me ask this. Do we have any baseball players here or not? Anybody on the baseball team? Well, you watch it. Is it possible to hit the ball with a bat such that the ball comes off slower than it was pitched? And what's that move called? Bryce, what's it called? What do? You bunt. You bunt. And when you bunt, you just hold the bat? No, you pull it back. You pull it back. A good bunter will let the ball hit it, and while the ball hits it, they pull the bat back. And hopefully, it dribbles into the infield and everybody scatters to get the ball. Well, if you allow the piston to move out while this is occurring, this is bunting all of those molecules. which means when those molecules strike that piston that's moving this way, they lose energy. They're bunted, they come off going slower. That would make the temperature go down. So making the piston come out, let the piston comes out means that would lower the temperature, but at the same time you heat it to raise the temperature. You gotta balance those two things. And do you think that's easy? No. No. Doing this is very hard. Operating an engine like this is very hard. This is, in principle, what you should do, but being able to do it's another thing. It's like saying, this is how you should do a pole vault. Yeah, well, you ask any of the pole vaulters how much they practice to be able to get all those moves right, and it's a nightmare. Okay? So in this case, you're bunting with the molecules. So what happens is this, though. The temperature is constant. That's what isothermal means, darn it. You can't say isothermal heat intake while the temperature goes up. That's a contradiction in terms. You can't say that. Temperature is constant. But some of the heat goes into the molecules and is immediately converted into work and stored in the flywheel. This is what you want. We loosely call it work. But we mean kinetic energy in the flywheel. Because once that flywheel is turning, just like you can skim up a toy and a friction toy and zin, 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 and let it go, that rotational energy can now be used to perform work. You could hook it up to something else, a machine, and have that energy do useful work. Is everybody with me? Now, you can't do this forever. This is a cycle. So what you have to do for the second, step 2, is you have to close off the back. So you close off the back, close it, and you allow the piston to continue to move out. You allow the piston to continue to move outwards, but you no longer put any heat in. You stop heating it. You allow this to expand. And because it is insulated, no energy is allowed to go in or out of the engine. That's called adiabatic expansion. Adiabatic means no heat in or out. I'll squeeze it in there. When you see the word adiabatic, I'll put a little star there, it means completely insulated, absolutely insulated so that no heat can leak in or out. What happens here? The piston continues to move out and bunt the molecules, so they wind up going slower, but because they're essentially pushing on this and doing work, more work is created in the flywheel. Actually not created, more heat is converted to work. Furthermore, we don't want this to go too low. Temperature drops to TC, and more heat is converted to work.
So if it drops PC, then more work's going to happen.
Let me restart the camera there, and we'll answer that. So the temperature drops to Tc and more heat is converted to work. Notice what we've done. We have converted heat into work. We have converted heat into work. That is what we want to do. We've taken some of this random, disordered internal energy and somehow organized it into the flywheel, actually, okay? Now, you don't want this to go too long. The temperature drops because the average kinetic energy here is going down because that energy is getting converted into organized kinetic energy, or what we call kinetic energy, in the wheel. So the temperature drops. But you don't want to let it drop too far. You want it to drop to the temperature of the cold reservoir. If it doesn't drop far enough, or if it drops too far, you can show using calculus that in the end, when the whole thing is done, you won't have as much work in the flywheel. So you have to stop this at the proper time. Was that answer your question? Or?
Yep.
Now, somehow we have to get back to the starting point. Somehow we have to get that piston all the way back in and have the temperature the same as it was at the start so we can repeat the cycle. If we just let this go around and start pushing in, what will happen is some of the work that we got out will get turned back into heat. Remember, you can take work and convert it into heat. You can do that when you rub your hands. And if we don't do anything and let it go all the way in, we will have added heat to it without letting this effectively have come out, and the temperature will be too high when we get back to the starting point. So if we just let it all go back in, the temperature is going to wind up being too high, and that's not going to work. We have to be able to get back to the starting point with the piston all the way in, and the temperature exactly the same as the hot reservoir. So this is where Carnot figures out that in order to do this as a cycle, we have this critical step, which is step 3. What you have to do in step 3 is open the back door. You have to open the back door and allow the piston to go back in. You have to let the piston go in. Now, what happens when you bat, not bunt, a baseball? Does it go off faster or slower? Faster. So if this starts to go in, what you're doing is you're batting the molecules and you're making them go faster. He says you're not allowed to let the temperature go up. Once the temperature gets to the bottom temperature, you must cool this. Now they show ice cubes in the textbook. You have isothermal heat discharge. At the temperature of the cold reservoir. By the way, for the first one, I should have said, I think I said it, but you had isothermal heat intake at the high temperature. Well, the high temperature was constant. You get to here, you have to discharge the heat at the cold temperature. So some of the work that's in here, some work is converted to heat, converted back. Now that by itself wouldn't be so bad. But the trouble is, this is discharged into the cold reservoir. This is one of the reasons you have to have a lower temperature. You must dump some of the heat into the lower temperature reservoir in order to get back to the start. Some work is converted back to heat and discharged into the cold reservoir. Whoops, so I can't spell here. So, can this engine be 100% efficient? The first name is Tyler, I thought it was. Tyler, can this engine convert all of the heat into work? No. Why?
I think my contention's on step 2, letting it drop to the temperature.
Yes.
It can't be exact.
You have to try to make it exact.
Yeah, but it can't be.
Why not? If you let this go far enough, you can drop the temperature almost as far as you want.
Well, it can't go to the cold reservoir exactly. It can't be too hot or too cold, as I remember.
That's what I'm saying. You've got to allow this to go to the point where the temperature reaches this temperature, and then you must immediately start the step.
Yeah, I'm saying that's extremely hard to do, if not impossible.
Bingo, that's why it's called the ideal. It's next to impossible to do. But there's the first thing, but I'm talking about this step. What is it about this step? Don't make this hard. That means it can't be 100% efficient. Can it convert all of the heat that it took in step 1 into work? What are you doing with some of the heat right here? You're dumping it out. This heat that you dump out did not get converted into work. Therefore, this engine cannot be 100% efficient. You cannot do it because you must discharge some of this heat. This heat that you discharged didn't get converted, and that means you're not converting all of the work into useful energy, into useful work. And no matter how you cut it, it's not only hard enough to do this, okay, to reach this, but also you cannot eliminate this step. This also means that since you have to have a flow of heat in order to move the heat, unless you use energy from some outside source, you have to have a temperature difference. You must have a temperature difference. So this says because some of the heat is discharged, the Carnot engine cannot be 100% efficient. That's the first big deal that comes out of it. It can't be 100% efficient. The ideal engine cannot be 100% efficient. This third step prevents that. And if the ideal heat engine can't be 100% efficient, no real heat engine, Tyler, can be 100% efficient either. Heat is some kind of a weird form of energy in that you can convert any of the other energy forms into heat. But if you now try and convert it back, you run into this problem. You can't convert it all back. And we're going to lead that to the second law of thermodynamics. Now, what is the fourth step? In the fourth step, this is step 3. This is step 3. Philosophically, step 3 is the most interesting one. Step 4 is we stop discharging this heat. Obviously, if you dump this heat for too long, that's definitely going to make it less efficient, right? That's definitely, you dump extra heat out. No, you don't want to do that. You want to do this as much as you got to. And then you stop. Then you stop. And once you stop, you close it off. It's adiabatic compression. So in this step, you allow it to continue to move in But now, because it's insulated, the temperature rises back up. And it has to rise back up such that when you get it all the way in, the temperature is precisely what the high temperature is, and you can start it over. And that's not easy to do either. During that step, more heat or more work is converted to heat. So, in the first two steps, you convert heat into work, but then you have to take some of the heat and dump it, and some of it has to be put back in to get back to the start. But, in the end, some of the heat remains permanently converted back into work or mechanical energy or whatever it is. The way I like to view this is exactly how I view this, is you all know how to use an ATM. Suppose you have one of those booths, you got a booth for an ATM, and you go in and you want to take $100 out of your savings account. And you go in and the door slams behind you and it locks. You're stuck in the booth. So you put your card in and you say, give me $100. So it spits out $100 and then you go to leave and the door will not move. You go, what? It says, please redeposit $25. What do you mean? What do you mean redeposit the money? Well, what do you mean? Well, it won't let you out unless you do it. So you grumble, you take $25, you make out a slip and you redeposit. Okay? That's this heat that got put back in. That $25 is still yours. You got to put it back in. You can make another withdrawal, right? Then you go out the door and it says it still won't let you out. And it says, please deposit $25 into the charity box on the floor. And you grumble some more and you realize it's not going to let you out. So you take $25, say I'll never come to this bank again. But you put the $25 into the charity account and finally you're out with your $50. Well, the $25 that got put into the charity account isn't gone. That's what's dumped in this step. This is the $25. It's there, but it's not available to you. It's not available for your use. The $25 or whatever that got put back in, well, you can get that in another withdrawal. This is how it is in nature. Nature says if you convert heat into, or work into heat, just like all these lights are converting electricity, they convert it to light, then the light gets converted into heat. If I try to run a heat engine and convert all of that heat energy back, I won't be successful. Some of it will always remain as heat. I can never convert all of it back. Heat is degraded energy. And there's nothing we can do about it. Any questions here? Now, this is all correct. Carnot tried to find a formula for the efficiency. Because if this is the best heat engine possible, then the only thing you should really need to calculate the efficiency is the two temperatures between which you are operating it. Well, he gets the answer wrong because he's using the caloric theory. But in the middle of the 1800s, they're able to correct for that, Lord Kelvin and others that were studying this, and they come up with the correct formula for the efficiency of a Carnot engine, which is as follows. Now, there are two ways to calculate it. There are two ways. One is the efficiency of any engine is the work out divided by the heat that went in times 100%. This is true for any heat engine, including a Carnot. Every heat engine can use this formula to work out its efficiency. Tyler?
Carnel or Carnot?
Carnot.
Carnot.
It's French. It's French. It's not
Is the T
Carnot.
seriously silent?
Huh?
Is the T silent?
Yes.
Oh my god.
Yes. Yeah. Well, you think French is bad, look at the English language, you know. When you see PH, you pronounce it like an F. Like a file. You know, file to hold medicine, it's P-H-I-A-L. Well, welcome to language, okay? Welcome to language. But here is another way to calculate it. This is only valid for a Carnot engine. It starts off being 100% efficient. The formula start 1 times 100 is what, folks? 100. But then you subtract off the cold temperature divided by the hot temperature. And you must use Kelvin, absolute temperatures. You can't use degrees Fahrenheit, you can't use degrees centigrade. You must use Kelvin, or absolute temperatures. Otherwise, it's not correct. Now, what temperature could you put up here in the top that would make this equal to 100%? If you had a reservoir at absolute zero, if you had a place that was at absolute zero and you put 0 in the top, what's 0 divided by anything? 0. And 1 minus 0 is 1. 1 times 100% is 100%. If you had a reservoir that was absolutely at 0, you could build a Carnot engine that was 100% efficient, except for one problem. The moment you discharge any heat into it, it's not at absolute 0 anymore. And we already said you can't actually reach absolute 0. So necessarily, even the best engine is less than 100% efficient, and that means that heat is fundamentally a different kind of energy. Let's stop right there. Have a great weekend. Keep your masks up and on, even if you are outside. If you are within 6 feet of another individual, you keep that mask on, which really means keep it on until you get to your dorm room, your room, or your car. Okay, have a great weekend. Bye-bye.